Hi, welcome to another lecture in control systems. In this lecture, we are going to look at stability of a control system. Okay, so how do we define stability? A stable system is a system that gives you a bounded output when the input is bounded. What that means is that if you have a system and you give a finite input to the system, the output should be finite. If the system does that, the system is called stable. If, however, for a particular finite input or for any finite input, the system gives you an unbounded output or an infinite output, the system is unstable. Now, of course, in practical systems, you cannot have infinite output. What usually would result is a destruction of your system or saturation. Okay, so those would be the things that would happen. So what we want to look at in this lecture is when do we start getting instability and how do we design systems that are stable. uh, right at the start, I want to talk about two different concepts. One is absolute stability, and secondly, relative stability. Absolute stability is basically telling, simply making a binary choice, right? Saying whether a system is stable or not stable. So we are just looking at a system and calling it, okay, this system is unstable, this system is stable. So that's absolute stability, which tells you whether the system is stable or not. Relative stability tells you how stable a system is. So there are two systems which are both stable, but we want to decide which system is more stable. And this will be especially important when you're designing a control system, let's say, and you have a choice between two design parameters. And you're just worried a little bit about stability. Both systems are stable, but you're just thinking over a period of time, as the parameters in the system change, the system may become unstable. So, which system is more likely to become unstable, right? The one that has higher relative stability is less likely to become unstable. So, stability can be talked about in absolute terms or in relative terms. Now, the idea of stability can be discussed by looking at this diagram. So, if you look at the first cone here, this one, the cone is absolutely stable, right? Even if you give a little bit of disturbance, you know that the cone is going to return back to its position. Now, this cone is just unstable. It probably can, in almost no circumstances, be standing in that way, right? So it's an unstable system. However, look at this system. Now, this system is stable. I mean, you can make the cone lie down, but even a little bit of disturbance is going to perturb its position and it's going to go into some other position. So this kind of system is neutral. It's neither stable nor unstable. So we either call it neutral, or you could say that the system is marginally stable. Now, you do not want to make systems that are either neutral or unstable, marginally stable or unstable, right? You always want to have stable systems. Why can't you design marginally stable systems? Basically, because any kind of variation in parameters may push the system into an unstable system. Okay, so uh, the necessary and sufficient condition for the stability of a system is that all the poles of that system lie on the negative real axis. Okay, so the real part of the poles are negative. Okay, it need not be in the negative real axis, it could be imaginary as well, but the real part of the poles should always be negative. Okay, so if all the poles are on the left hand side of in the pole zero diagram, left hand side of the imaginary axis, the system is stable. It's as simple as that, the rule. Okay, if the poles are on the right hand side, the system is unstable. the system is not, uh, yeah. And if the poles are on the imaginary axis, the system is marginally stable or the system is neutral. Okay, so all our solutions to figuring out whether a system is stable or not, we are going to do the very simple thing that we're going to try to find out the poles of the system. And if the real parts of the poles are negative, great, our system is stable. Otherwise, even if one of the poles is not on the negative, uh, does not have a negative real part, or it has a positive real part, then the system is going to be unstable. So I thought in the last two slides, I'll just talk about two practical examples. They're kind of interesting, kind of gruesome examples of when stability goes haywire. So here's a system, here's a building. This is the Techno Mart. I think it is in Seoul in Korea. And on the 12th floor of this building, there's a gym, and around 23 people gathered there, and they started doing some kind of an aerobic exercise, which is, I can't remember the name of the aerobic exercise, but it is a cross between taekwondo and boxing, and it involves a lot of rhythmic movement. And as these people started doing this rhythmic movement, the building started vibrating. And it was vibrating so much that experts had to be called in to find out the cause. And the cause was then uh, localized to this gym and to this exercise that these people were doing there. So basically, a bounded input, some kind of thumping and jumping around by these people on the 12th floor of the building, caused the entire building to kind of start vibrating. Uh, as far as I know, if the building didn't collapse and nothing happened, so that's good. But the next example, uh, things were not so good. So this is the Tacoma Narrow Bridge. I'll just play the video. And as the wind started to blow, you can see that this bridge is actually starting to shake. And it's really amazing. This is a bridge on which there is a tar road. And we'll just see that in a moment, right? There's a tar road, and you can see that there's a car here. And this bridge is actually vibrating just because there is some wind flowing. And you can take a look at the vibrations. It becomes more and more, and the output of this system, output of this bridge in response to the pressure variations of the wind becomes higher and higher. Okay, and you can see that, whoa, uh, it's vibrating quite a lot. I'm not sure what these people are doing in the bridge. They need to be far away. uh, and you can see that this bridge is, and the amplitude of the vibrations increases so much that the bridge eventually collapses, right? That's just to show you how important it is that our systems are stable. I'm not saying that the designers of this bridge didn't consider stability. I'm sure they did, but probably they missed something, and the wind was at a particular frequency that caused instability at that particular frequency or for that particular input.